In the secret corners of our universe sneaks a quiet power that sets everything around it moving. Not light, not make any difference. However, a strange substance that we have scarcely started to unwind, dark energy. For a long time, it has evaded the handle of our best personalities, gathering dust on the racks of hypothetical cosmology. Today, we stand on the limit of discovery, and new proof recommends that we might have been mixed up about the actual idea of this puzzling power. Might it at some point be that our thought process was constant is really evolving before our eyes? Go along with us as we dig into the profundities of space, directed by the most recent information from the Dark Energy Spectroscopic Instrument, DESI, and embark on a journey that could reclassify how we might interpret the universe. Music. To ensure we are all on the same page, we should first discuss bionic acoustic motions, or BAO. These waves, set in motion by serious tension waves in the early universe, now act as grandiose yardsticks, permitting space experts to precisely measure immense grandiose distances. This complex, vast cooperation, an inheritance from the introduction of the universe after the Big Bang, gives us a remarkable vantage point to examine the texture of the universe in such an enormous scene. The Dark Energy Spectroscopic Instrument, otherwise known as DESI, turns into a guide of sorts. Equipped with a variety of 5,000 finely tuned fiber optic sensors, DESI is setting out on fantastic errands to meticulously map the three-dimensional places of tens of millions of universes and quasars. This aggressive endeavor is planned not exclusively to chart the inestimable geology, but also to reveal insight into the shadowy power known as dark energy, which is believed to be the impetus for the universe's speeding up development. Light is first reflected from the telescope's 15-ton primary mirror and then hits 6 huge focal points that furnish DESI with a wide, highly engaged perspective of the sky, covering a region about multiple times the size of the full moon. These focal points are housed in a gadget that can be changed within thousandths of a foot to keep the focal points adjusted. Subsequent to going through the arrangement of focal points, the light from the universe comes to the fiber optic links at the DESI central plane. At the finish of the telescope are 5,000 positioning robots, each conveying a solitary optical fiber, modified to move to pre-chosen arrangements of cosmic focuses. This computerized robot connection permits DESI to target arrangements of thousands of galaxies at the same time. Optical strands, which act as DESI's eyes, guide light from the universes down the length of the telescope to 10 spectrographs. These spectrographs are then used to acquire extremely precise spectra of these objects and produce redshifts for the different galaxies and quasars in the dataset. Every fiber optic sensor in the DESI cluster is a communication channel to the universe, directing light from galaxies and quasars across billions of light years to the heart of the instrument. Mechanical positioners ensure the gem-like accuracy of every strand's arrangement to the heavenly objective. The strands, each as thick as a human hair, are not simply passive recipients. They are the endpoints of a complex optical path that starts in the depths of space and finishes in the gadget spectrograph. Here, the caught light is dispersed into its constituent tones. When DESI examines the sky, it gets faint reverberations of far-off universes, each carrying an enormous history, kept in bill. These estimations, like the Big Morse code, are painstakingly decoded and analyzed to reproduce the history of the expansion of the universe. Through this careful process, DESI provides a brief look into the past, tracing the development of the universe from its tempestuous youth to its current more measured growth. The significance of BAO in this grand story can't be overemphasized. Cosmologists are using this instrument to chart the development of the universe with exceptional precision. This technique, based on the basic physics of the early universe, offers a dependable reason for testing our comprehension of cosmology by refining our models of the hidden design and arrangement of the universe. From the perspective of DESI, BAO is changed from a simple inestimable reverberation to a powerful discovery tool. So, how might the mission help enlighten the most obscure corners of space? Let's expound on BAO. Imagine that the universe is a huge sea in which sound waves once freely. Engendered through the hot, thick early universe, these were not sound waves as we realize them, but rather pressure waves produced by the intricate cooperation between radiation and matter in the early universe. This cooperation led to what we presently call baryonic acoustic oscillations, an artifact design engraved in the conveyance of cosmic systems across the universe. These waves, in the texture of the universe, give us a standard ruler for estimating enormous distances with remarkable accuracy. In the early universe, there was a contest between gravity, which was arranging matter, and radiation pressure, which was pushing it apart. This interaction created motions similar to sound waves. When the universe adequately cooled to form atoms, and radiation separated from matter, these motions froze completely still, leaving a perceptible pattern in the distribution of galaxies. The peak of these motions, at a time span around 150 million light-years, serves as our cosmic ruler. This astronomical ruler allows cosmologists to measure the expansion of the universe in a novel way. By analyzing the distance between galaxies and contrasting it with the expected separation from the baryon acoustic oscillations, BAO, researchers can work out how much the universe has expanded since light was emitted from these galaxies. This method also allows for a direct estimation of the pace of expansion of the universe at various points in time, providing clues to the nature of dark energy and its effect on cosmic development. Thus, the Dark Energy Spectroscopic Instrument, DESI, can use BAO measurements to produce an exceptionally detailed map of the universe's expansion at different ages. Situated atop the 6,880-foot peak of Mount Lemmon in Tucson, Arizona, which offers panoramic views of space, DESI utilizes a powerful array of mechanical fiber optic sensors in its mission to understand the accelerating expansion of the universe. Looking into the night sky, the instrument captures the light of millions of galaxies and quasars. By measuring the redshift of this light, DESI can determine how quickly the universe has expanded at various times. The instrument's accuracy allows it to detect subtle BAO imprints in the large-scale structure of the universe, turning these measurements into a detailed three-dimensional map of cosmic development. This map is not merely an assortment of data points. It is a timeline of the history of the universe, from its early, denser state to its current accelerated expansion. By examining the observed BAO scale at different distances and, thus, at different times in the universe's history, and comparing it with what we expect from cosmological models, DESI tests our understanding of dark energy and the fundamental nature of the universe. The beauty of the DESI approach lies in its ability to investigate distinct ages, offering a window into the universe's expansion over billions of years. This vast period allows researchers to track whether dark energy remains constant over time or evolves. So, what was the purpose of this study? As we know, the accelerating expansion of the universe, a phenomenon in conflict with the normal slowing effects of gravity, has revealed the presence of a mysterious force known as dark energy. This discovery, made in the late 1990s through observations of distant Type Ia supernovae, revolutionized our understanding of the universe. Dark energy, which makes up about 68% of the total energy content of the universe, has a repulsive force that counters the gravitational pull of matter, thereby accelerating cosmic expansion. It was this discovery that laid the groundwork for the lambda cold dark matter, lambda CDM, model at a time when the observed properties of the universe seemed contradictory, and there was no consensus on the composition of the universe's energy density. The model successfully accounted for a wide range of cosmic phenomena, from the large-scale structure to the behavior of distant supernovae. Scale construction of the universe to anisotropy in the astronomical microwave foundation notwithstanding the intricacy of the universe. The light LDA cold dim matter model is somewhat basic and described by a little arrangement of boundaries. These include the Hubble constant, the densities of dark matter and dark energy, and the initial conditions for the presence of the universe. The predictive force of the model permits cosmologists to test its legitimacy with observations, for example, the distribution of galaxies and the cosmic microwave background. The Dark Energy Spectroscopic Instrument has given new insights into the strange nature of dark energy by examining in excess of 6 million cosmic objects at tremendous distances and various ages. DESI gives solid estimations of the expansion history of the universe with previously impossible accuracy. This broad database, covering a redshift range from 0.1 to 4.2, allows us to recreate the expansion of the universe exhaustively and uncover the impact of dark energy throughout cosmic time. Quite possibly one of the most captivating outcomes from the first year of DESI observations is the sign that dark energy may not be a static force, but rather may evolve. This speculation originates from the subtle inconsistencies observed between DESI measurements and the predictions of the lambda cold dark matter model. Specifically, the data gathered in this study suggests that the boundary of the dark energy equation of state is near being predictable with the cosmological constant. However, if we expand the lambda model and add a time-varying dark energy equation of state, the DESI data, in combination with the cosmic microwave background or type Ia supernovae, certainly demonstrates a deviation from the model. This implies that the impact of dark energy may not be consistent, but may change with time. This tendency endures in various combinations of datasets, showing deviations from the lambda model. The data acquired in the study, particularly the discovery of dark energy, represents a serious test to the lambda model, traditionally founded on the description of dark energy as a constant part. The detailed planning of the large-scale structure with the instrument provides data that may necessitate changes to the standard cosmological framework, specifically the parameters for the modern value and rate of change of dark energy, indicating a variety of the dark energy impact with time. Such a deviation from the static lambda assumption of dark energy, represented by the cosmological constant, would require a basic reassessment of the model's capabilities. The results of the paper have significant ramifications. If the dark energy equation of state does indeed change, this could lead to a major modification of our ideas about the development of the universe and its ultimate fate. Such a paradigm shift would not only refine our understanding of dark energy but would also affect the broader cosmological models that describe the composition, structure, and evolution of the universe. To accommodate these ideas, cosmologists may need to explore new theoretical frameworks or update existing models to account for a time-varying dark energy component. This may require developing more complex models that account for the dynamical behavior of dark energy or updating our understanding of the interactions between dark energy, dark matter, and other cosmological parameters. One captivating option is to consider a dynamic form of dark energy with a changing equation of state, as opposed to the cosmological constant lambda, which remains constant throughout cosmic time. A core field that evolves could provide hints to the observed discrepancies. This model allows the effects of dark energy to change, possibly in line with the evolving equation of state of dark energy, as referred to by the study. The possibility that dark energy interacts with dark matter or other components of the universe also opens up an intriguing viewpoint. Such an interaction could lead to noticeable consequences on cosmological scales, potentially explaining the changing nature of dark energy. Another interesting, though radical, proposal is the idea of early dark energy. This model suggests that dark energy played a significant role not only in the late universe but also in its early phases, leaving imprints on the anisotropy of the cosmic microwave background and large-scale structures. This might offer a new perspective through which to interpret the findings, particularly if dark energy impacts have been woven into the fabric of the universe since its dawn. The feasibility of each of these hypotheses depends on consistency with observational data and various scales, from the cosmic microwave background, isopiastic sequences, and supernova distances. The contribution of this project lays the groundwork for future research in cosmology, as DESI continues to deliver an exceptionally detailed map of the cosmic web during its 5-year mission. Moving forward, several future tasks are expected to dig deeper into cosmological mysteries. These future efforts will likely build on DESI's discoveries, using advanced observational techniques and theoretical models to further investigate dark energy and its effects on the universe. A discussion between study members Shash Shad Nayan and Andrew Text Font Rara emphasized the collaborative nature of this search, underscoring the integration of DESI data with other observations to create a more complete picture of the universe's evolution. Such a cooperative approach is essential for developing our understanding of dark energy and its role in shaping the ultimate destiny of the universe. Although the instrument's results challenge our current cosmological models, DESI's project is far from finished. It is merely a prelude to a much larger cosmological story, and standing at this threshold, we are reminded of how much we still have to learn about the construction of the universe.